Review Lesson 3, Composition of Functions. Our objectives for today's lesson are 1. Find the composition of two functions. 2. Determine the domain of the composition of two functions. And 3. Evaluate a composite function at a specified value. Composition of functions. That's our vocabulary. So how do we define a composite function? So here's the mathematically precise definition. So we have two functions, f and g, and you put them together and make them work in order, one after the other. So the function given by f of g of x, you read this, f of g of x. That's how you read that. F of g of x, and you can write it this way, f of g of x. This is the composite of f with g. In other words, we're putting the two functions together and making them work one after the other in a particular order. So which function goes to work first? The inside function goes to work first. And which function goes to work second? The outside function goes to work second. To help you understand this idea conceptually, consider that you are working with your little brother, and your job, as given to you by your parents, is to fold the laundry. Okay, so your little brother is younger than you, so maybe he's not so good at folding. So you say, I will be the first function. I will be G, and my job will be to take something that comes out of the dryer and fold it. So you take something that's kind of messed up and you fold it and make it neat. So your output from your function, you're the function, is to have a nicely folded shirt or pants, etc. So the outside function, the second function, would be your little brother. And his job is to take your output and he's going to put it in a drawer or someplace in the closet to store it. So he takes whatever you give him, which is a folded shirt or a folded pants, and he's going to take it and put it in the drawer or somewhere in the closet. So that's the idea with composition of functions. You have two different functions with two different rules, and each one does something. They go in order. One goes to work first. It takes an input. In your case, you would take something that's messed up, a messed up shirt, and you would fold it, and that's your output, a folded shirt. You give that to the second function, which is your little brother, and he's going to take the folded shirt, and he's going to put it where it belongs. That would be the output from his function. The folded shirt is where it should be, in its rightful place. So let's go ahead and take a look at the rest of the definition. So this is the definition of composite function, and we explained it conceptually. So now the domain of the composite function is the set of all input values in the domain of the function that goes to work first. Remember, the inside function goes to work first. So the domain of the composite function is the set of all x in the domain of the first function, or the inside function, such that the output values from the first function can be taken as input values for the second function. So going back to the example with you and your little brother, the domain of the composition of the two of you would be all the clothes that come out of the dryer. Why? Because anything that comes out of the dryer, you're the first function, you can fold it. So your output will be a folded shirt or folded socks or folded underwear or a folded jacket, whatever, right? And then your little brother can take whatever you fold and put it where it belongs. So the domain of the composite function would be everything that comes out of the dryer. So here is our first example for today. Example 4, given f of x is equal to 2x minus 3 and g of x is equal to cosine x, find each composite function. So we have f of g of x. The first thing that you want to do is write it this way, f of g of x. So going back to what we just talked about, g of x is the first function, or the inside function, and f of x is the second function. So if you look at the function g of x, the input is x, and the output is cosine x. So the output from the first function will be cosine x, which would then be given as the input for the second function. The output from your function in the conceptual example is a folded shirt or a folded pair of pants. That is then given to your little brother. So the output from the first function here is cosine x. The input for the first function is x. The output is cosine x, which is then given to the second function. And what does the second function do? Well, your little brother put the folded clothes away. But in our example here, the second function is going to take what it gets and multiply it by 2, so it'll do 2 times what it gets, which is cosine x. It gets cosine x from the first function, and then subtract 3. And you're done. That's all you've got to do. Now for the other composition, you've got g of f of x. So you're going to write g of f of x, and you're going to do this. The difference between the two is that in the second composition, the function f goes to work first. So if you look at the function f, the input is x, and what will the function f do with the input? It will multiply it by 2 and subtract 3. So the output from the function f is 2 times x minus 3. So that will then be given as an input for the function g. And what will g do? What does g do? Whatever it gets, it takes the cosine of it. So you're going to have cosine of 2x minus 3. So that's an example for finding composition of functions. So here is number 59. Find the composite functions f of g and g of f, and then also find the domain of each one and answer the question, are they the same function? Is f of g the same as g of f? So you're going to find f of g of x, which would be f of g of x. And what is the function g of x? It's the square root of x. So you have f of the square root of x. And again, the input for the function g is x. The output is square root of x. This will now become the input for the function f. And what does f do? It takes an input and it squares it. So you get x. Now, g of x is square root of x, but I meant to say this. I meant to say, let's go ahead and find g of f of x. How do you find g of f of x? So you're going to have g of f of x. So in place of f of x, you're going to write x squared, because f of x is x squared. Again, here's how you think. You start with your first function, which is f. The input is x, and the output from the first function is x squared, which becomes the input for the function g. So what does the function g do? It takes the square root of that, and you get x. So these are inverse functions. They undo each other, and both of them will give you x. However, we want to think about what is the domain of each, because you might think they're the same function, but they would only be the same function if they also have the same domain. Do both of these functions have the same domain? If you just look at the end result, you might think, well, both functions have the same domain. X can be any real number. However, you do have to follow the chain of the composition. So when you're thinking about the domain of a composite function, you have to think in this way. It's a set of all x in the domain of the first function, such that the output values from the first function will be in the domain of the second function. So the first function in f of g of x is g of x, and the domain of g of x is only what? From 0 to infinity, including 0. The output values are positive numbers because you're taking positive square roots, and you can square any number, so there's no problem with f squaring whatever g gives it. But because the first function is square root of x, the domain is only from 0 to infinity. But for the other composition, the first function is x squared, and you can square any number. You can square any number. So the domain of f is all real numbers, but then you also have to think, when I square a number, what do I get? Either 0 or a positive number. Does that work for the second function? It does, because the second function is square root, and you can take the square root of any non-negative number, and the output values from the first function will be non-negative. So you can give any number to the first function f, but since the output values from the squaring function are always going to be non-negative, you can give any output from the first function to the function g, because all the outputs from the first function are non-negative. So you can give the function f, the first function, any number. F can square any number, and the outputs of f will always be non-negative, so that will work for g, because you can only take square root of non-negative numbers. And for that reason, because you start with f and you can give it any number, the domain here would be from negative infinity to positive infinity. And because of the difference in domains, we say the functions are different. So here we have number 57. Given f of x is equal to the square root of x and g of x is equal to x squared minus 1, evaluate each expression. So our first function here is g, and our second function is f. So you're going to have f of g of x. The input for the function g is x. The output is x squared minus 1. So you have f of x squared minus 1. The second function will be evaluated at the output from the first function. So what does the second function do? You can see that f of x will take an input and take the square root of it. So we're going to have the square root of x squared minus 1. So that's the composition of the two functions. For the other composition, f would be the first function and g would be the second function. So you have g of, what is the input for the function f? It is x. What is the output? It is the square root of x. So you'll have g of the square root of x. Square root of x is the output from the first function, which will then be given as the input for the function g. And what does the function g do with whatever it gets? It squares it and then subtracts 1. So you'll have the square root of x squared minus 1, which will be x minus 1. So when you think about the domain, you actually have to think by following the chain of the two compositions. So here, the first function is g of x. You can square any number and subtract 1. So the domain for the function g of x is all real numbers. But then you also have to think, what's going to happen when I give an input to the function f, which is going to take the square root of this. There are some output values from the function g that although it works for, there are some output values from the function g that f cannot take as input values. So what that means is there are some values of x for which g of x will be negative, and you cannot take the square root of a negative number. So what values of x would make g of x negative? If you want to look at the graph of g of x, you can see that very clearly. The graph of g of x is a parabola opening upward, and you can see that for these values of x, between -1 and +1, g of x will be negative. And you cannot take the square root of a negative number. So when you think about the domain here for f of g of x, it has to be from -infinity to -1, not including, well, you could include -1, and then union from +1 to infinity. And if you look at the other function, g of f of x, what is the domain? The first function here is square root of x, and for that square root function, we know that x has to be greater than or equal to 0. The output from the square root function is going to be any non-negative number, but g can take anything. It can square any number and subtract 1, so it doesn't really matter. So the domain for the second composition will be from 0 to infinity. So how do you find f of g of 1? Now that we have found f of g of x, which is right here, we can use that to find f of g of 1. It would just be the square root of, the input will be 1, so we will have 1 squared minus 1, which would be the square root of 0, which would be 0. If you want to find b, we have g of f of 1 How did we find g of f of 1? Well, we already have the function g of f of x, right? That's right here. This is the function g of f of x. So to find g of f of 1, you're going to use the function g of f of x and evaluate it at x is equal to 1. So you have 1 minus 1, which will be 0. We'll take a look at two more examples. So the next example that we want to look at is g of f of 0. Again, you're going to use the function g of f of x, which is, of course, right here. And you're going to have g of f of 0. So all you need is substitute 0 for x, and you get 0 minus 1 is negative 1. And we're going to look at our last example for this set. We want to evaluate f of g of negative 4. What is f of g of negative 4? F of g of negative 4, you're going to use f of g of x. That's our function, which is right here. So f of g of negative 4 would be the square root of negative 4 squared minus 1, which is going to be the square root of 15. So that's how you do those problems. For the last example for today's lesson, we'll take a look at number 63. The difference between number 63 and the problems that we've looked at already is that for the problems that we've looked at so far, algebraic rules were given for the functions f and g, or some kind of a rule. Maybe it was a trig function, but a rule was given for what f was and what g was. And we found f of g of x or g of f of x, and in the previous example, we were able to evaluate composite functions at certain values of input, certain input values. The difference between all of that and this problem is we're not given a rule for f, and we're not given a rule for g. Instead, we're given graphs for f and g. But we can still do a, b, and c, also d, e, and f, but I will show you a, b, and c as examples. It says here, use the graphs of f and g to evaluate each expression. If the result is undefined, explain why. So we will go ahead and take a look at what A, B, and C is asking us to do. So for part A, we want to do f of g of 3. The key to doing this problem is to remember what this means. It means you've got f of g of 3. So this is like coming home from school, and you need maybe like 2 different keys because you have 2 different locks. Maybe you need to unlock the gate, and you need to unlock the door to your house. Okay? So you've unlocked the first lock, which was to rewrite f of g of 3 like this. But now the second lock, how are you going to unlock it? The key that you need is to understand function notation. The name of the function is g. The input for the function is 3. So g of 3 is the output from the function g when the input is 3. How do you get that? Remember yesterday's lesson. You look at the graph of g, and you look at the input of 3. The input of 3 is right here, where x is equal to 3. And you have this point on the graph of g with coordinates 3 for x and negative 1 for y. So g of 3 would be equal to negative 1, because you have 3 and g of 3, which is the output, which is of course equal to negative 1. So you have f of negative 1. So when you give an input of 3 to the function g, it gives you an output of negative 1, which is then given to the function f. Just like you take something from the dryer and you fold it, and you give the folded shirt to your little brother, and your little brother puts it away. So the function f is going to take what it gets as an input, which is the number negative 1. In the case of your little brother, it would be like a folded shirt, and he's going to do his job. F is going to do the job that it does, which is represented by the graph here. So when the input is negative 1, what is the output? You look at this point on the graph of f, which has an x coordinate of negative 1 and a y coordinate of positive 4. So this point is negative 1 and f of negative 1. Remember, f of negative 1 is the y coordinate. So what is f of negative 1? It is equal to 4. And that's the answer that you have. So now we're going to take a look at 2 more, B and C. So we've got B here. And what we have is g of f of 2. Again, the key to doing this is to understand that you have a composition of 2 functions. That's what you need to understand first. Second, you need to understand that the first function is f of x, the inside function, and the second function is g of x, the outside function. Third, you've got to understand function notation. So the input for the function f is 2, and the output is f of 2. 4, you've got to get that information from the graph of f. So here's the graph of f. When the input is 2, x is equal to 2, what is the output? look at this point on the graph of f. It has a y-coordinate of 1. So this point has coordinates 2, 1. But again, remember, 2 is the input, the function is f, and the output from the function f, when the input is 2, is given by f of 2, which is, of course, the same as the y-coordinate. So f of 2 is equal to 1. So you have g of f of 2, which is 1. That's the output from the first function, which is then given to the second function. That would be like a folded shirt that you give your little brother. So your little brother is going to put that folded shirt away. In this example, g is going to work with the input of 1, and g is going to give you an output. So how do you find what that is? You look at the graph of g. Where is x is equal to 1? Right here. So you have this point on the graph of g with coordinates 1, negative 2. So that's going to be 1 and g of 1. Remember, g of 1 is the output, which we now know from the graph to be negative 2. So g of 1 is negative 2, and that's the answer you have. We're going to conclude with our last example for today, part C. So here is part C. We've got g of f of 5. Now, notice that the instructions state if the result is undefined, explain why. So let's see what happens here. Again, you've got to understand that you have a composition of functions. That's the first thing. The second thing is that f is the first function and g is the second function. Third, you've got to understand that for the function f, we're looking at the input value of 5 and what is the output value. So here is 5 for x, and you're looking at this point on the graph of f, which appears to have a y-coordinate of negative 5. So you have 5, negative 5, or 5, f of 5. What is f of 5? It's negative 5. So you have g of negative 5. The only problem is, now you're working with the function g, and understanding function notation, negative 5 is the input for the function g, but when you look at the graph of g, you can tell what the domain of the function g is. The graph of g starts here at x is equal to negative 4. And it ends here at x is equal to positive 4. So the domain of the function g is from negative 4 to positive 4. Negative 5 is the input value for the function g. It's outside of the domain, so the function can't do anything with it. We don't know. It's outside of the domain. So this is undefined for that reason.